So this project was also my master thesis project that I've been working on for the last year. And as a start, we can have a brief overview of what the ecological footprint and biocapacity are. So they are a set of sustainability indicators where on one side we have the ecological footprint, which measures the demand society places on nature. And then on the other side, we have biocapacity that measures the supply or nature's ability to regenerate resources and to sequester carbon. And both metrics are measured in the same unit, which is the global hectare. And they include several different land categories, including fishing grounds, built-up land, cropland, grazing land, and forest land. And then on the ecological footprint side, we also have forest carbon uptake, which illustrates anthropogenic CO2 emissions as the area of world average forest that would be required to sequester them. And then on the biocapacity side, we also consider that forests are sequestering carbon. And then the aim of my research is focused on biocapacity itself and specifically integrating wetlands as a component. And the scope of my research is to develop the process towards including wetlands in national accounting. And how I do that is by developing 3 case studies of 3 countries, specifically Iceland, Sweden, and Germany. And I aim to create the entire time series that biocapacity is available for, including wetlands, which is from 1961 to the present. And I used primarily global data because biocapacity is produced for over 200 countries, and it requires globally harmonized data that is comparable across countries and regions. And wetland reporting is rather limited, so it doesn't have coverage of all of the world's countries. It's relatively limited how many countries report on wetlands. And then my research questions are framed around the data availability itself, because that's one of the reasons why wetlands aren't included in the ecological footprint and biocapacity and many other frameworks, is that they're quite difficult to measure and there's not historically been a lot of data available. But this is rapidly changing because we have far greater computational power now than in the past, and new method development like remote sensing, which helps in studying ecosystems like wetlands. And then my second research question is, how sensitive is biocapacity to variations in area or different area estimates? And then also, how does productivity weighing impact biocapacity? And with regard to wetlands, there's a few things that we should keep in mind. And one of them is that they provide many ecosystem services, including climate regulation, nutrient removal, habitat provision. They also mitigate floods and reduce damages in extreme weather events. They contribute to groundwater recharge and many more. And many of these ecosystem services we will not be able to illustrate in biocapacity, which is not to say that they're not important. They are, but it's a rather complex ecosystem, as all ecosystems are. And then also wetlands provide a lot of indirect and non-use value. So they're less so useful as an ecosystem that provides direct resource extraction. And they're valuable also just through their existence. And then they're also estimated to cover between 3 and 21% of terrestrial area, depending on the estimate. And this is, of course, a very, very large range. And this really depends on the definitions that are used in the estimate, also the monitoring period and limitations in observation and modeling system. And the different estimates of wetland area can either be complementary or partially overlapping, or they can also entirely disagree depending on these factors. And yeah. So this is important to keep in mind, and it's because wetlands are an ecotone, so they occur in this transition area between terrestrial and aquatic systems. So it's very difficult to draw the exact boundary when a certain territory is or isn't a wetland, and then they also have a lot of different vegetation. So it's not necessarily it's very complicated to define, and they're quite variable in different areas of the world as well. So this is one of the main challenges of this study is that there's inconsistent definitions across wetland area datasets and across different areas of the world. And then there is also not really standardized global reporting for area or productivity that covers all countries of the world. So then we are limited to using estimates rather than national reporting. And ecological footprint and biocapacity uses national reporting where possible, but this might not be possible in the wetlands case specifically. And this comes with some other limitations, of course, because global estimates can generally be based on a more coarse data set rather than on than a lot of ground-based and field measurements of the ecosystem itself that national reporting is frequently based on. And then also another challenge is that the area time series usually start at around 1990, which is because of the availability of satellite data, and there's not so many historic records of wetland area. So when we're extrapolating backwards to 1961, we don't necessarily have a lot of data for this extrapolation, or the data that is available is difficult to validate because many countries don't have historic records, and wetland area change has by no means been linear because there's been quite a lot of drainage and conversion of wetland ecosystems, in particular before the 1990s, because historically wetlands were perceived as more of a nuisance and as not providing any use to society because their indirect and non-use value was not recognized widely. And then also wetland benefits to society accumulate over time. So stocks are very important to assess in a wetland context, but biocapacity is a flow-based metric. So how I approach this very complex ecosystem is through the ecosystem service of climate regulation. And for that specifically, I can say that wetlands are a carbon sink. They provide low but persistent net ecosystem productivity, which over time results in the accumulation of carbon stock, and they hold about 20-30% of global carbon stocks, which peaks at around 60 degrees north. And then they can also be a carbon source, depending on the circumstances, especially if they are drained, because then this carbon stock rapidly disintegrates, and that results in the release of a lot of emissions. And they're also a natural source of methane and other greenhouse gases. And in the context of biocapacity, we would be focusing on wetlands as a carbon sink, and I use that as the productivity metric that is integrated in biocapacity to calculate yield factors. And once again, biocapacity doesn't include stocks, but rather only flows. And then the wetlands as a carbon source would belong on the ecological footprint side under emissions there. And we don't capture methane in the framework at the moment. So with that, we can go to calculating biocapacity, which is calculated by multiplying area in hectares with yield factors, which weigh land within the land category itself. And they specifically normalize national productivity by global productivity. And this is how we calculate the world average hectare. And then we multiply by equivalence factors, which are a weighing between land categories based on agricultural suitability. And this is how we make the land categories comparable to each other by converting them to this common unit, the global hectare. And in my research, I selected 3 different area scenarios based on 3 different data sets to see how sensitive biocapacity is to different area estimates. And then I also had 3 different scenarios for yield factors, which I'll go into a bit later. And for equivalence factors, I set the equivalence factor of forests to be equal to that of wetlands, because equivalence factors are currently calculated based on agricultural suitability, and wetlands are not really agriculturally suitable land. So that is why I include this assumption. And this is also the approach that is used for other land use types that are non-agricultural, like fishing grounds and built-up land, is that there's an assumption tied to them to relate them somehow to one of the other land categories. And with that, we can look at some different area data sets. So these are just area estimates for different country in percent and in hectare. And I looked at different types of data sets, some that are national, that are based on extensive field measurements, and more local knowledge, and then top-down that are based more on satellite classifications. And this is two different approaches to generate wetland data sets. And the reference scenario I selected is this Climate Change Initiative land cover dataset, which is also published by the FAO. And the FAO is the source for a lot of the data that biocapacity is calculated from. And it's also very beneficial that it's an annual data set. So there's a yearly update of wetland area. And this is a satellite-based classification. And then I also used, as a second scenario, the Global Lakes and Wetlands database, the second version, which is a static database, which has a rather long compilation period. And it combines 25 different global data products, which include historic wetland maps, wetland probabilities, and different types of satellite classifications to generate one wetland dataset with over 30 classes. And this is a very commonly used data product for global wetland analyses. And then I also used a national dataset. And these are usually semi-dynamic, so they're updated once every few years by national authorities, and they're also usually based on a standard classification. And that can be treated more as the ground truth of, and usually is the highest resolution data available. And I also mapped these different data sets just to see how the wetland area distribution looks. And we can see that it's not only that the estimates are different, but also which areas are classified as wetlands. And of these three, the middle one is the most different, and this is this Global Lakes and Wetlands database. And this is because this data also includes these historic wetland maps and probabilities, so it doesn't necessarily relay well to present-day land use. So it can include some historic wetland signals, and it also includes maximum inundation extents, which is why it can really emphasize the river plains, so the areas around rivers, which this is not really any type of validation per se, it's just an attempt to understand how wetlands are interpreted through different data sets, and all of these data sets are very useful for different purposes. But for the purpose of biocapacity, we would be looking for a data set that relates closer to present-day land use, which is why the reference scenario is beneficial, that is closer related to the national data. And for Sweden, it's a similar case, that in the middle, in the global lakes and wetlands, we have a more of a diffuse signal, whereas in the first and third, the national and the reference scenario, we have more of a discrete signal, but of course it's not a perfect match. So that is our area scenarios. And then going into yield factors, I base yield factors on net ecosystem productivity, and specifically on a machine learning model published in 2025, which used machine learning to extrapolate over 800 measurements of net ecosystem productivity from many different areas in the world. And then as a second scenario, I used the data compilation of that same model. So before it had gone through the machine learning process. And then I separated by these by climate zone, and I attributed each country to the climate zone that it primarily belongs in. And then I also used that same compilation to calculate the yield factors by country. And calculating yield factors by country based on net ecosystem productivity can be very challenging for a great majority of countries, because most of the net ecosystem productivity measurements come from 10 countries. And then there's about 15 countries that have a few measurements available, at least in this data compilation. And then there's many countries of the world that would have no measurements at all, which is why it can be useful to use machine learning in this type of scenario when there's a lot of gaps in global data. And here it is interesting to see that the scenario based on the machine learning model itself has the lowest values for all three countries. And one of the explanations for this is that there is rather limited data for tropical wetlands. And even though we're not looking at tropical wetlands at all in these countries, the machine learning model extrapolates the available tropical measurements, which have relatively high NEP and also a lot of variation to these areas where there are data gaps, which shifts the global average higher, and that results in lower estimates for these countries, among other reasons. And then another interesting thing to see here is that in this data compilation, there were only 3 data points identified for Iceland, which results in this uncharacteristically high NEP estimate, and then also on an uncharacteristically high yield factor. And that is more of a cautionary tale that we should be very careful to not base wetland productivity estimates or yield factors on very few samples, because wetland productivity can be extremely variable. And also an important thing to note here is that this is not necessarily all the data that exists in the world. Many countries measure wetlands, and there might be more data points available, but these might not be published. So these might not be included in any published studies or repositories. So whenever global wetland study is made, this data might not necessarily be available for it. So this is the case for Iceland also, is that national authorities here do have a lot more data on net ecosystem productivity, but this wouldn't have been available at the time of this analysis. So with that, we have all three components that we need, and equivalence factors are based on forest equivalence factors, as I mentioned before. So with that, we can already calculate biocapacity, and this is the process of calculating area, multiplying it by yield factors, and then the third column is multiplied by equivalence factors. And here we can see that these northern latitude wetlands, they do have relatively low productivity relative to the global average. So this constrains their total hectares when we're doing this conversion. And then we can already look at how biocapacity, including wetlands, looks for a reference scenario. So for Iceland, about 4.3 of national biocapacity would be coming from wetlands. And because Icelandic biocapacity is dominated by fishing grounds, since it's a relatively small country with a relatively very large fishing grounds, if we remove fishing grounds, it would amount to 18% of terrestrial biocapacity. And then for Sweden, we have 0.9%, and for Germany, 0.1%. And because our area dataset is only available from 1990 onwards, I used a global wetland reconstruction to extrapolate backwards, and I calculated a yearly loss rate from this reconstruction that I applied to my last available year up to 1961. And what was interesting to see here is that, for instance, for Iceland, this global reconstruction hadn't found any data for Icelandic wetland coverage. And in this particular study, they used a lot of historic land conversion records, ditch excavation, peat extraction, in order to try to calculate how historic wetlands might have looked like. And because they didn't identify much data for Iceland, according to this reconstruction, Iceland hasn't lost any wetland areas, but in fact, we do know that around 47% of Icelandic wetlands have been drained. And there is, specifically for Iceland, a ditch excavation time series that is available per year. So this could be corrected specifically for the Icelandic case. But that's important to know that there's a lot of uncertainty of how big wetlands were historically. And this reconstruction, it does give us a way to extrapolate backwards, but it might not necessarily be accurate. And in many cases, for many countries, there wouldn't necessarily be enough national data to even validate whether it's accurate. But it's still one approach that can be applied consistently across the globe. And with that, we can already look at the entire biocapacity time series for the different countries, as well as our different scenarios. And what is interesting for Iceland is that wetland biocapacity does change from 4.3 to 6.9%. But especially in the last case, where we had this yield factor based on very few data points, then it shifts it quite dramatically. So this is, again, more of a cautionary tale. That wetland productivity is very, very variable. And then for Sweden, what is interesting to see is that even though Sweden does have relatively large wetland areas, it also has very, very productive forest ecosystems that are managed for productivity. They're also a very important part of the country's GDP, and these can constrain wetland contributions further just because wetlands are relatively low productivity ecosystems. And then for Germany, we have very low wetland biocapacity as expected because the majority of German wetlands have been drained. And then only in the second scenario, which was based on this Global Lakes and Wetlands database, which also captures its historic wetland signals, we have a 24-fold higher wetland biocapacity, but when we represent that in total biocapacity, it's only a 1.5% increase, again, because other land categories are far more productive and they also have larger areas. So with that, we can go to some limitations of this study. So for one, there is still limited data availability for wetlands, and the data that is available might not be representative. There are many regions of the world that have far poorer data availability, for example, the tropics. So in that sense, it can be helpful to focus on global area estimates and on machine learning because these can provide some gap filling for these areas of the world that have less data available, but still it's a large improvement since, for example, 20 years ago when none of the data that I used was even possible to generate. And then also an important limitation is that there's an absence of carbon stocks and land degradation, and these are very important to consider in a wetland context, but they can't really be represented in biocapacity currently. So it's very important to be transparent of how wetlands are included and that these particular themes are not there, and if possible to revise some normative choices so that we might be able to include these in future analyses. And then also a further limitation is that equivalence factors are based on agricultural suitability, so they can't be calculated for non-agricultural land. So here it's interesting to consider whether there are other approaches for calculating equivalence factor in the future or also to assess different types of assumptions. And then it's also challenging to define a productivity metric for biocapacity. I focus on net ecosystem productivity, which is more approximating carbon sequestration and that ecosystem services that wetlands play in climate regulation, but you could also approach it for biomass production just within the wetland plants, which would be represented for net primary productivity, but both of these units are not necessarily consistently reported on across the globe, so you would run into much of the same challenges because there is also this balance in what data is available when you would be constrained to using global models, which have a rather coarse resolution, among others. And to summarize, this project established a process for wetland integration in biocapacity, but it's still important to note that biocapacity and other aggregate indicators are simplified representations of complex ecosystems, so they are our starting point. But you always need to look at more metrics and more data to understand the full context, so they cannot capture every aspect that is important about land category. And then the wetland integration is nevertheless very valuable as a public communication tool because this signifies that wetlands are important to consider in a sustainability context, which was not necessarily the case historically, because wetlands were not really perceived as valuable. So it's very important that they are included in frameworks like biocapacity and many others, which they are omitted from. And then there is some limited utility for management decisions and policy, because biocapacity does favor higher productivity ecosystems. So it would be very easy to draw a false conclusion if you only view biocapacity that wetlands should rather be drained and turned into croplands, because that would increase biocapacity, because you would have a more productive land, and cropland also has the highest equivalence factor, so it's weighted higher. And then some next steps would be also to develop case studies for additional countries, because these are only 3 examples. And it would be quite interesting to see, for example, what biocapacity would look like for tropical countries, or for other countries with large wetland areas that are not in this northern latitudes with their low productivities. So tropical countries would have like the other end of the productivity range. And this also to assess some alternative approaches, for example, using another productivity metric, another source, different equivalence factor assumptions or approaches, and then also to test the integration in the national ecological footprint and biocapacity accounts production process, and then eventually, hopefully, in the long run, to include wetlands in national reporting. So thank you all for listening to this presentation, and